Hello everyone, I am Munot and welcome to the School of Physics. So today we are going to study about wave motion. Right. So first let me tell you the basic terms of wave motion. Yeah, wave is that easy to do. Wave is one of the most easiest chapter, and I guarantee you'll get full marks in waves in physics. So because I am teaching you. So let's begin. So first of all, let me teach you how to write a wave equation. Okay, so this is something what a wave equation looks like. So this is the y direction and this is the x direction. A wave equation is the representation of motion of y, the position of y with respect to the position of x. So it is usually a sinusoidal curve and it is written as y is equal to a sine kx minus omega t. Okay, kx minus omega t. So this is the representation of y with respect to x and t. So representation of y with respect to x and t. So this is the wave motion. So what is this A? A is the amplitude. So A is the amplitude, that is the maximum direction. So it is a sinusoidal curve. So this is the maximum y at which this wave can go, and this is the minimum y, which is also equal to minus a. So this is minus a, this is plus a. Okay, so this is a sinusoidal curve. Now distance between two crests, distance between two consecutive crests or two consecutive troughs is called lambda, which is the wavelength. This is called lambda. This is the wavelength. Now how much time did it require to travel lambda distance? So the time required to travel lambda distance, is the time t, which is the time period. So lambda distance is traveled in t seconds. Okay, so how much time is traveled in 1 second? So in 1 second, lambda upon t is the distance traveled, and we know what is the distance traveled in 1 second called? It is called the velocity. So wave velocity is equal to lambda by t. Now 1 by t is equals to frequency. Now what is frequency? So how much is the number of oscillations in t seconds? So the number of oscillation in t seconds, is 1. In t seconds the wave covers 1 oscillation. T is also the time period required to cover 1 oscillation. So in t seconds the wave covers 1 oscillation. So how much in 1 second the wave covers? So in 1 second the wave covers 1 by t oscillations, which is equals to the frequency, which is also called as, frequency is also called as the number of oscillations covered in 1 second, which is 1 by t. Okay, so you got the basics, we covered the basics. Now what is this k and omega? Okay, so we'll write it down here. What is k? I'll just rub it off. So k is the phase change. In traveling 1 unit distance, and omega is the phase change in traveling 1 second. So I'll write it down here. So suppose for traveling lambda distance, the phase change is 2 pi. Okay, so for traveling 1 unit distance, the phase change is 2 pi by lambda, and this is k. Okay, and for traveling t seconds, the phase change is 2 pi. Okay, so for 1 second the phase change will be equals to 2 pi by t. Okay, and for say delta x distance, how much will be the phase change? For delta x or for x distance, the phase change would be, for the x distance, the phase change would be 2 pi by lambda into x, and for t time, the phase change would be 2 pi by t into time. Okay, so this is what the phase change is. So that is how we come up with our equation fx f ax plus minus bt. So suppose this is the equation of our wave, like we have written a sine omega kx minus a sine omega kx minus omega t, right? So this is a sine kx minus omega t. Now this is how the wave equation is if in the form of f ax plus minus bt. So at any time if it is given that the wave equation is in the form of f of ax plus minus bt, then we write the wave velocity. The wave velocity, okay, wave velocity is equal to coefficient negative of coefficient of time upon coefficient of distance x. So this is a very star formula for any function ax plus minus bt given as the wave equation. The wave velocity, that is wave velocity, is written as dx by dt. It is equals to negative of coefficient of time upon coefficient of x. Now what is the comparison between the particle velocity? So what is the particle velocity? Particle velocity is dy by dt, okay, and wave velocity is dx by dt. So is there a comparison between dy by dt and dx by dt? Yes, there is. So we have to remember that the particle velocity is equal to negative of omega by k of the wave velocity dx by dt, wave velocity dx by dt, and particle velocity dy by dt. So this is also written as the relation, the particle velocity is equal to negative of omega by k into wave velocity. All right, so we have done this thing. Now let us recall the wave equation, which was a sine omega x minus kt. If we have to find the particle velocity from this equation, all we have to do is differentiate. So what we do is dy by dt is equal to a omega cos of omega x minus kt. So we just have to differentiate. Okay, moving on to the next topic. What is the energy? Okay, so we'll have a very important topic. Here I'll prove that the intensity. What is intensity? Can you tell me the definition of intensity? Intensity is directly proportional to amplitude square, which is a very important result for all the wave equations. So intensity is directly proportional to amplitude square. So kinetic energy per unit volume. Kinetic energy per unit volume, average, is equal to potential energy per unit volume. We have to remember this result. It is half rho omega square a square cos square kx minus omega t. Okay, so this is what we have to remember. Kinetic energy and potential energy per unit volume is equal to half rho omega square a square cos square kx minus omega t. When we do an average, so average energy per unit volume becomes half rho omega square a square, half rho omega square a square. Now the next thing that we do is, this is energy per unit volume. So suppose this is the cross section S, and in one distance, so this is the cross section S, and in one second the distance traveled is the wave velocity v. Okay, so what is the energy? Energy is equal to half rho omega square a square into volume in 1 second. This is the velocity, v is the distance in 1 second, and s is the cross section area. It is equals to s into v. Now intensity is equal to energy per unit area per unit time. Okay, so intensity is equal to energy per unit area per unit time, which will be equal to, for 1 second it will be equal to half rho omega square a square into velocity. So this is the formula for intensity. Considering the rho, omega and v are constant, we get this result as I is directly proportional to A square. Very important result for waves. I is directly proportional, that is intensity of energy is directly proportional to amplitude whole square. Now we talk about superposition. Okay, suppose we have two wave equations, two sine wave equations, and we superimpose both of them. We have studied this result in SHM as well, but what we are going to do is, I'm not deleting this, I'm not rubbing this, because we are going to use this result. So in superposition, suppose I have a wave y1 is equal to a1 sine omega t, okay, and another y2 is equal to a2 sine omega t plus 5. Okay, now superimposing both of them, y1 plus y2, suppose we get a sine omega t plus theta. So there will be no change in phase in superimposition. In superimposition there is no change in phase. So this is, so what is A? We know A is equal to, A square is equal to A1 square plus A2 square plus 2A1 A2 cos of theta. Now what is theta? We know theta, this is suppose A1, this is suppose A2, okay, and this is suppose some angle theta at which we have A, or we can say capital A, we can say at which we have capital A. Now tan theta is given by, and this is the angle phi between both of them, so tan theta is given by A2 sine phi upon A1 plus A2 cos phi. We remember this formula from SHM superimposition. Okay, so as we remember, I is directly proportional to A square, so we write I and I square, okay, I under root I square, or say I under, or say I, okay, we say I is directly proportional, is equals to under root I1 square plus under root I2 square, okay, plus 2 under root I1 under root I2 cos of theta. Okay, so this is I square, or sorry, under root of I ka whole square. Okay, now from here we get A max. A max, when this angle is proportional, A max will be A1 plus A2, and A minimum in the superposition will be equals to A1 minus A2. Okay, and we can also write I max. Now this is the important result. I max is equal to under root I1 plus under root I2 whole square. Okay, and I minimum will be equals to under root I1 minus under root of I2 whole square. So this is the result, this is the important result from superposition. A and I result, I is directly proportional to A square, and this is what the result that we get. And right, now we study the transmission and reflection, the condition of transmission and reflection. Okay, so what happens in transmission and reflection is, in transmission and reflection, what is asked is what is the amplitude that is reflected and what is the amplitude that is transmitted. Okay, so suppose we have a string and we have another string connected with this string. Okay, now this is the amplitude initial that we have sent, and now this is the amplitude. After some time this goes, so this is the amplitude transmitted, and there will be also a amplitude reflected. So suppose the velocity initially was v1, now the velocity after this transmission is v2. So there will be very two simple formulas. We have to remember these two simpler formulas. However, there will be no change in frequency or omega. So frequency and omega will be constant, but there will be a change in amplitude. So what is this is the reflected amplitude, and that is the transmitted amplitude. So the reflected amplitude can be written as, this is the velocity after transmission, this is the velocity before. So this is v2 minus v1 upon v2 plus v1 into amplitude initial. Okay, this is formula number 1. Now we have formula number 2, which is amplitude transmitted is equal to 2 times of v2 upon v2 plus v1 into amplitude initial, which is the amplitude transmitted. So direct question on amplitude reflected and amplitude transmitted will be asked. Okay, now we have a very important formula, which is equal to, which is whenever there is a tension in the rope, then what is the velocity? Wave velocity. So wave velocity whenever there is a tension in the rope is written as under root t by mu, which is mu is the reduced mass, t is the tension. So we have a rope, we have a wave, and this is the tension in the rope. Okay, now I'll be writing this formula in a lot of different ways, and all of these different ways are asked directly in the exam, and this is one of the most used formulas of the wave motion. Okay, so this can also be written as T by rho into A, where rho is the density and A is the area. This can also be written as under root of E by rho, where E is the modulus of elasticity. So E, whenever it is a solid, becomes R gamma, that is stress upon strain. Which can also be written as F upon A upon delta L upon L. So this is stress upon strain. When this is a liquid or a gas, it turns out to be bulk modulus. Bulk modulus, as we know the formula, delta P upon delta V by V. And in case of gases, for isothermal, bulk modulus is equal to pressure, and for adiabatic, bulk modulus is equal to gamma, that is adiabatic pressure constant into pressure. So then when we put this here, it becomes, for gases this formula becomes wave velocity is equal to under root of P by gamma, P by rho, or gamma P by rho in terms of, so this is for isothermal and this is for adiabatic. Okay, gamma P by rho. Now rho, P by rho can also be written as nRT upon M. P by rho can also be written as nRT upon M, and this is a very star and used formula. This formula is used a lot. Directly you will get questions. So this is nRT upon M into gamma. Okay, so this is when there is a tension in the string, or whenever there is a modulus of elasticity connected, or it can also be turned into a bulk modulus question, where you will be given the change in pressure and change in volume, or it can be converted into just the effect of pressure upon density, or the adiabatic constant upon density. So this is a very important formula, turned and twisted into many forms, and this is one of the most used formula of wave motions. So friend, this was our chapter on wave motion, a small lecture on wave motion. I hope you will be able to do all the questions related to wave motions. Please subscribe to my channel so that I can make more videos like this. Thank you so much for watching this video. Thank you.